Good morning from Vienna. Good afternoon to everyone. Thank you very much for this invitation. Also, thank you very much to all the speakers to have accepted to be part of this today. I'm very honored to speak to you and to have the pleasure to introduce you to the world of isotopes if you haven't heard about it 2 weeks ago. So before I'll talk about applications, I wanted to let you know a little bit about the International Atomic Energy Agency. You might know the IAEA mostly as a nuclear watchdog, but the IAEA is more than that. And it works with member states and multiple partners worldwide to promote safe, secure, and peaceful nuclear technologies. Currently, the IAEA has 172 member states and headquarters is in Vienna. And we have a few other offices, but no regional or country offices. So the IAEA's mandate is to seek to accelerate and enlarge the contribution of nuclear techniques to peace, health, and prosperity. And you can't really have good health without nutrition, and this is why the IAEA has a program in nutrition. And this is part of the pillar of science and technology. The other two important pillars of the IAEA is verification and safety. So coming to the nutrition program at the IAEA, its aim is to enhance the member state capabilities to combat malnutrition for better health throughout life. We have three main themes: early life nutrition, prevention and management of non-communicable diseases, and diet quality and nutrition security. And since what we do is so specific and we support the use of very specific techniques, we always seek to complement the work of bigger players in nutrition. And we try to see where we can add value by encouraging the use of stable isotope techniques. So where can isotope techniques be used? They can be applied in monitoring and evaluation of programs. For instance, programs that promote optimal infant and young child feeding practices, or food fortification programs, or supplementation interventions. They can also be used in programs to prevent and treat moderate and severe malnutrition. But we need more in order to improve the nutrition situation than just implement those proven nutrition interventions. We need to really make sure that these programs are working and having an impact. So we need better tools for program evaluation to make sure that there is impact. But generally, we need still to work on capacity building to enable that countries can tackle malnutrition. And this is where the IAEA comes in. We can help with better tools to obtain more accurate data, and we can help with capacity building. So now I have talked about isotopes a few times already. And before I continue, I would like to remind you what isotopes are. So each element has several isotopes. And those isotopes have the same number of protons in the nucleus, but they have different number of neutrons. And that's why they have different atomic masses. There are also electrons in the nucleus, but they don't really contribute to the mass. So looking at an example, right. So here's an illustration of the different isotopes of hydrogen. So hydrogen has 3 isotopes. So the most common one, most abundant in nature, is protein, which has just 1 proton. And if you add a neutron, you get a slightly heavier isotope, that's deuterium. But it's much less present in nature. We call that abundance. It's much less abundant in nature. So both of those are stable isotopes. If you add another neutron to deuterium, you get tritium, which is radioactive, decays, and emits radiation while decaying. So in the nutrition studies, we use the stable isotope deuterium that's not very present in nature. Next slide, please. So besides hydrogen, other interesting isotopes for nutrition are carbon and oxygen. And again, we use here the ones that are less present in nature, carbon-13 and oxygen-18. Other staple isotopes that are being used in nutrition assessments are for elements such as nitrogen, calcium, iron, or zinc. But we can also use hydrogen or carbon to label compounds such as vitamin A. So in summary, staple isotopes are safe and emit no radiation. They occur naturally. We all have them in us and they are in the environment. Because we have them in us, we need to always take a baseline sample before we administer additional amount of isotopes. And we use the staple isotopes for nutrition assessments that are less present in nature, so we can use them as tracers. They're suitable for all ages and they can be used in community settings. So what kind of assessments can you use isotopes for? So you can use them to assess protein quality, amino acid digestion from foods, or you can use them to look at micronutrient bioavailability, in particular of iron and zinc, in the context of food fortification or biofortification. I'll talk about it later. You can also use them to assess vitamin A body stores, for instance, to understand the effect of interventions to prevent vitamin A deficiency. I'll talk about it more. But you can also use them in the context of environmental enteric dysfunction to understand whether micronutrient absorption is impaired due to living in unsanitary conditions, or you can use them to assess breastfeeding practices and body composition. We talked about this 2 weeks ago. And then they can be used to assess total energy expenditure. I'll talk about it later. That can be used to estimate energy requirements or to validate measurements of physical activity or dietary assessment tools. And then a nuclear technique can be used to assess bone mineral density, which could be important in the context of osteoporosis prevention. Of course, there are many more, but those are the ones we support as the IAEA. So how do we support this use of isotope techniques and how do we support our 172 member states? We have two main mechanisms. One is the coordinated research projects. We define a research question in consultation with experts. A call for proposals is put together, and then a small group of research institutes come together for 4 to 5 years. We provide small annual grants and bring them together regularly for coordination meetings. So those research projects are very much driven by us, meaning the small team of nutrition specialists sitting in Vienna. Then we have the technical cooperation program that's driven by the member states. It's based upon request from the member states. So it functions in a biennial planning cycle. Every 2 years, member states being asked to submit project ideas. And the main aim here is to build and strengthen the capacity in the use of isotope techniques. So what's provided is training, expert advice, equipment, but also support for sample analysis or data management and analysis. So now I would like to share with you some examples of the use. I'll start with vitamin A. And here is an example of a research project that we supported in the last 5 years. It just ended on optimizing nuclear techniques to assess vitamin A stages. And we were focusing on the isotope method in the context of high vitamin A intake. So 8 countries participated. It was a collaboration with the Gates Foundation. And the main takeaways is that the isotope method works even in contexts where vitamin A consumption and total vitamin A body stores are high. That's something we had to confirm. We also found that it's reliable in children suffering from mild or moderate inflammation, and tested shorter protocols that are equally feasible and accurate. And in parallel, we supported a regional project through our technical cooperation program that used isotope techniques to assess vitamin A status of children susceptible to infection in 11 countries in Africa. That was over the last 6 years. Total vitamin A body stores were assessed alongside serum retinol and RBP and some infection markers or inflammation markers. Some countries are still analyzing samples, but we have already one publication from a country and others are under preparation. So watch out for that. So here I want to show you the added value of using the isotope technique. You will hear more about this project from our last speaker, Professor Sherry. But just here to show you, it's fortified extruded rice was given in Thailand to school children. And it was looked at serum retinol and using the isotope technique at total body vitamin A stores. So you see that the vitamin A body stores doubled during the intervention, but the most commonly used method here, the serum retinol, did not show an improvement. So had we not used the isotope technique, we would have concluded that this intervention was not efficient. But here the isotopes show a different picture. But again, you hear more about it from Professor Sherry. So just in a nutshell, how does that method work? You have to take a baseline blood sample. Then you administer a dose of vitamin A labeled with a staple isotope. You let the dose mix with the vitamin A body pools, and then you take a follow-up blood sample. The analysis of the samples is conducted by mass spectrometry, and then you can estimate total vitamin A body stores. Professor Sherry will tell you more about it. So moving on to iron isotopes. How can you use iron staple isotopes? Here's an example from Morocco, where the IAEA supported an iron isotope study to confirm high absorption from an iron fortificant that was added to wheat flour. And for decades, Morocco had added elementary iron to wheat flour, an iron fortificant that's not very bioavailable. So it wasn't effective, and iron deficiency did not reduce. So now this a different iron isotope with higher bioavailability is now being used after conducting this isotope study, and hopefully this will make a change. Here's an example from Senegal that was just published, how you actually influence iron absorption if you consume at the same time of eating fortified wheat bread, a polyphenol-rich tea, and how much you decrease iron absorption. That's actually something they found in Morocco as well. If you look here at the table, so this shows a fractional iron absorption from this wheat-based meal, the bread, and if the tea was consumed at the same time as the bread, that's the kinkeliba here, the iron absorption, the fractional iron absorption, is much reduced if you compare it to consumption of the bread with water. So, and that was shown in mothers and their young children. So, important message, I guess, always don't consume tea at the same time of eating fortified bread or a fortified meal. You can also use the iron isotopes in the context of biofortification. Here's an example from Rwanda where biofortified high iron beans were tested. So in this example, unfortunately, it couldn't be confirmed that high iron beans have a great potential to improve the amount of iron absorbed because of high phytate and, again, high polyphenol, which limited the absorption. So how is this being assessed? Again, we'll hear more about it from Professor Prashanth later on. But here you add the iron isotopes to test meals, and the design varies depending on your research question. But just as an example here, the iron isotopes are being added to test meals, but before the study participants consume the test meal, a baseline blood sample is taken. And then again, after 2 weeks, a second blood sample is taken to assess the retention of the isotopes in the blood. So the iron is analyzed by mass spectrometry, and the ratios of the stable isotopes before and after dosing are compared to determine the amount of iron that was incorporated into the red blood cells. Also, show you an example of biofortification for Asia, here, India. So this is biomill, higher content of iron and zinc. And then this worked very well. The absorption studies showed that the amounts of iron and zinc absorbed are greater from the biofortified millet than from non-biofortified millet, and that young children, if they eat that as a major staple food, could meet their physiological requirements. I wanted to point to a review article on the use of staple isotopes in micronutrient nutrition that covers vitamin A, iron, and zinc, if you're interested to see more examples. So now I'm moving away from the micronutrients to energy expenditure, and the next speaker will cover more of it. So I'll just give you a short introduction. And I wanted to show you our database, our global database on doubly labeled water with measurements of energy expenditure, over 6,700 measurements from more than 20 countries. So what are measurements of energy expenditure? Well, they used to determine the amount of food or calories a person needs to function. So quite important data that we have gathered here, and we launched that database about a year and a half ago. So what is doubly labeled water? The doubly labeled means we're using two isotopes at the same time, deuterium and oxygen-18. And that method is really the only method that enables measurements of energy expenditure in free living subjects as they continue their normal activities. So a participant drinks a dose of deuterium and oxygen-18. The body water is enriched with deuterium and oxygen-18, and as time progresses, the deuterium leaves the body only in body water, urine or sweat, whereas the oxygen-18 leaves the body much faster in both water and carbon dioxide. So here is the elimination of deuterium, and the dotted one is the one of oxygen-18. And the difference in these two elimination rates is a measure of carbon dioxide production, from which you now can calculate energy expenditure. And here you have an example of a sampling protocol, but again, we'll hear more from the next speaker. Just to give you an idea of the value of putting data from small different studies together in one global database, you will be able to answer the really big questions with that. For instance, what are important factors that influence energy expenditure? How do energy demands change over the lifetime of a person? Or how do they differ between sexes and ethnic backgrounds? Or has energy expenditure actually declined over the duration of the obesity epidemic? Or is it something else that is important here? And then also, what's the impact of growing sedentary lifestyles on dietary needs? So all really important questions that the small individual studies couldn't answer. But here with this pool, you have the chance to understand a lot more. So before ending, I would like to summarize the different services that IAEA provides. So we develop guidance documents, we provide education and training, we help compile and host databases, as you have just seen, and we conduct interlaboratory studies. Here are some of the guidance documents. We have 8 different ones on different isotope techniques. We have also e-learning modules that complement the guidance documents. We produce fact sheets and flyers to disseminate information on the use of isotope techniques in nutrition assessments. And then you can learn about our latest activities in our biennial newsletter. You can subscribe to it. So I hope some of you will decide to join us and join the isotope community. And all the material, the guidance documents, the fact sheets, the flyers can be found and downloaded for free from our resource website, the Human Health Campus. So soon, the Human Health Campus will look different. We launch a new version, and it's a different look and feel, and we've added content. And please make use of this and download all the information you need. Thank you very much.
Yep. So I'd like to talk about the measurement of total energy expenditure using the double level water, its history, standard method, application, and the IAEA database. As in a first presentation, the Cornelia introduced stable isotopes and its application for human nutritional studies. And the measurement of total energy expenditure using the double leveled water is one of the applications. As Cornelia explained, the double level water can assess total energy expenditure of daily living without any masks or indirect calorimetry rooms. So double level water is very unique tool for nutrition, physical activity, and health studies. My presentation includes 5 parts. At first, I will talk about short introduction about the total energy expenditure and double level water. So total energy expenditure, TE, is the amount of calories burned by the human body in one day. TE is composed of basal metabolic rate, diet-induced thermogenesis, and activity energy expenditure. People with diseases or injuries may have higher resting energy expenditure compared with healthy people because many kinds of biological stress require additional energy metabolism than normal resting energy expenditure. While metabolic stress may increase energy expenditure, injury and disease are usually accompanied by decrease in physical activity that more than compensate for the increase result from stress. So TE in patient may therefore be similar or less than that in a healthy individual. So double level water is premixed water of 2 stable isotope enriched waters. One is a heavy oxygen enriched water named water oxygen 18, and the other is a heavy hydrogen enriched water named water deuterium. Because 99% of water O18 is very expensive and unnecessary for normal human studies. 10 or 20 atom% of water O18 is used to the double level water study in human. So stable isotope naturally exist in human body as well as any object in our planet. A human whose body weight is 50 kilograms has 137 gram of carbon-13, 68.6 gram of oxygen-18, 12.3 grams of oxygen-17, about 5 gram of nitrogen-15, and about 1.5 gram of deuterium. The doubly level water method increases the concentration of the oxygen-18 and the deuterium in human body on a temporary basis. Now I will talk about the history of the double level water method. Human body burns energy using the inspired oxygen and expires carbon dioxide, CO2. Inspired oxygen was measured by André Lavoisier in 1970s. And then Atwater and Rosa made a direct calorimeter loom in 1905. Since then, energy expenditure were calculated by measuring inspired oxygen and expired CO2. And the W level water is a very unique tool method to calculate total energy expenditure. Premixed water of water 18 and water deuterium is administered orally, and a spot sample of urine, blood, or saliva was taken before and after the dose. Then the elimination rates of two isotopes are measured, and expired rate of CO2 and TE was calculated from the difference between those elimination rates. The double level water method was invented in the 1950s by Dr. Nathan Rifson and colleagues at the University of Minnesota in the United States, but was only used on the small mammals and bats until the early 1980s, mostly because of the cost of the isotopes. The reduced cost of the water 018 and the advancement of the analysis allowed researchers to examine total energy expenditure in human. And in 1982, Dr. Shoran and Van Santen firstly measured the TE in human using the double level water method, followed closely by several other groups in Texas, the UK, and the Netherlands. In the Shoran and Van Sante's first experiment, they conducted with only 4 healthy adults in 1982 because of the cost. In 1986, Dr. Shora validated the double level water method against indirect calorimeter, the metabolic chamber loom, and established the modified equation, result of a careful consideration of the human biology and physiology. These studies are breakthrough of the double level water method and in human nutrition, physical activity, and health studies, but the number of the double water studies had been still low because the cost of the water 18 was still very high. And the double level water method required the specific devices, the isotope ratio mass spectroscopy. However, use of the method has stabilized at about 120 papers per year since 2000. Now the cost of water 18 is much lower than one used to be. So I will talk about the standard method of the double level water. So at first, we premix the water deuterium, the water 018, and orally administered the double level water. Then urine, blood, or saliva sample are taken before dosing and after dosing. In general, after 3 or 4 hours, the excess isotope concentration will reach at maximum level. And total body water can be calculated from this difference. Both stable isotopes eliminate from human body with exponential function. After converting log transformation, the elimination difference was occurred between the two isotopes. The deuterium eliminated as only water, and the oxygen eliminated as water and the carbon oxide. So we can calculate the elimination rate of the CO2 using the double level water. So I will talk about a fixed 2-point double level water protocol, and the take baseline sample before dose and the dose double level water, and take 2 samples after dose, and take 2 samples the last day, like 7 days after or 40 days after dose double level water. There is another method named the multi-point double level water protocol. And the samples are analyzed by the stable isotope ratio mass spectrometry. And the elimination rate of the CO2 was calculated with the equation. And in final, we are using the Wyer's equation, and we calculated the TE. And we have a website, double level water calculator, in University of Colorado right now. So I'd like to talk about the applications. The application of the double level water method is, for example, the assessment of energy requirements, examination of validity of the food questionnaires, and assessment of the activity energy expenditure with combination of the measured RAE, and the examination of validity of devices or questionnaires assessing the daily physical activity. Dietary self-reports are unreliable and they underestimate the actual energy intake. So double level water measured the TE is essential for establish the EER. So this is an example for examine the relationship between double level water calculate energy intake and frailty in older adults. And this is an example to examine the validity of wearable devices using the double level water. The findings suggest that most wearable devices do not produce a valid measure of TE, and further studies are required. And we can calculate the activity energy expenditure. And if we compared with the physical activity questionnaires against the double level water, most of the questionnaires is not met good criteria. So also future studies are needed. Lastly, I'd like to talk about the IAEA double level water database. And this is a website that the initial idea was floated in 2014 in Tokyo, Japan, and the formally launched on the 11th December 2018, and still growing. And now over 6,700 participant data was available. And there is a many contributor, and you can be a contributor if you have a double level water data. And if you interested into be, please contact me or John Speakman. And as Cornelia presented, um, the, this DLW database, we can examine a lot of questions which we cannot um, examine in each small individual experiment. The current IAEA database is grossly lack of data from Asian countries. So data entries and the W level water experiments are needed in Asian countries. Thank you very much.
Availability technique, which is using stable isotopes, like both my previous speakers who spoke at length about the use of stable isotopes. And this is a technique that we use to measure iron bioavailability using stable isotopes of iron. And I would not go into what isotopes are, but the stable isotopes that we are going to talk about are already present on Earth, and it is inside your body, inside every plant and animal that we eat as food. And stable isotopes are perfectly safe, and they do not emit any radiation. There's often a confusion with people when we talk about isotopes. They get confused between stable isotopes and radioisotopes, and they often think that stable isotopes also emit some form of radiation and is harmful. So I would like to touch on this point that stable isotopes is absolutely safe to be used in children and pregnant women, and has no health hazard of any nature. And since it's already present in your body, it doesn't cause any issues on using them in studies with human subjects. So as we saw in the previous two presentation, isotopes can be of any element. They can be light isotopes like carbon, hydrogen, and nitrogen and oxygen. You can also have isotopes of elements such as iron, zinc, selenium, and so on and so forth. So here you have an example of iron isotope. There are 4 stable isotopes of iron, that is iron 54, iron 56, iron 57, and iron 58. And as I said, these are naturally occurring stable isotopes, and they are already present in your body. So if I were to take a blood sample from you today and measure the isotopes in iron isotopes in your body, you would have the iron isotopes, all these 4 iron isotopes, which are at varying levels of these isotopes are present in the body, which is similar to what is present on Earth. And since you are eating the plants and animals that are grown on Earth, which has the same composition, you would also have the same composition. And so what we do is we buy enriched iron isotopes from suppliers, and then we add this enriched isotopes through your food to measure your iron bioavailability. And when you consume that enriched food, depending on the absorption of that enriched food, you would change the isotopic ratio within your body. And by understanding the extent of change, you can then quantify the absorption of the iron from the food that you were testing. And also you can document different kinds of interaction of various components within the meal. So this is the broad principle on which we are using to understand iron bioavailability by isotope ratio that's already in your body by using enriched tracers in your food. So the important question is, why do we have to do these studies? And like several low and middle income countries in Asia and other places, there is a large burden of anemia in many countries. And like India, we have a huge burden of anemia and iron deficiency. And this burden is primarily because of poor bioavailability of the diets that is consumed in the Indian context. And that may be true in several other countries where the diet is very monotonous and does not have a varied composition of fruits and vegetables, and also meat and poultry foods coming into the diet. So in such settings, the bioavailability of iron would be very poor, and that in turn would cause a huge burden of anemia and iron deficiency in the population. And if you want to understand what are the ways in which you can design dietary interventions to overcome this burden, you need to have a mechanism to measure bioavailability. And using stable isotopes is one of the best methods to do so. So the iron bioavailability is defined as the amount of iron that is absorbed in the body from the food and then utilized in the body. So the diet usually comprises of plants and plant sources such as vegetables. And in poor countries, the amount of fruits and vitamin C containing foods may be very low, and also meat and fish and poultry products may also be very low. In such settings, the iron intake into the body would be very poor. And for us to understand the dynamics of how the diet is playing within the population, iron bioavailability will become very useful. So before we start getting into understanding how the iron bioavailability studies are done, we need to understand what are the various iron pools within the body. And in humans, we can say that most of the iron is distributed into the red blood cell mass, the myoglobin in the muscle, and ferritin and hemosiderin that is stored in the liver are the main primary pools of iron in the body where iron gets stored. And it is we need to have an idea of where the pools of iron are in the body. And we also have to have an idea of the metabolism of iron. And this is not this is true not only for iron but also for any other mineral or element of interest. We need to understand how the body gets the nutrient of interest. In this case, iron. Iron is obtained only from the diet. We cannot get iron from anywhere else. And we need to understand how that iron moves within the body and how the absorption moves the iron into the body, and how much of that iron is moving into the body. Where does the iron go? Where is the iron utilized? In the bone marrow, it is used for producing red blood cells. And what is the cycle time it takes for the iron to get utilized, packaged into red blood cells, and come out into circulation? So you need to have a fair understanding of the metabolism of the element within the body. And in the case of iron, we need to understand that the iron is coming primarily from the diet. And so the a mixed diet may contain iron from plant sources, iron from animal sources. And along with that, maybe we spoke about, my previous speaker spoke about the tea consumed along with fortified food. So that's a dietary inhibitor. If you add vitamin C containing food, they are dietary enhancers. So all of this comes from your diet. And depending on how much of an enhancer or how much of an inhibitor is present, they would interact with this iron in the iron that is present in the food to make it available to the body. So the iron that the absorption of iron occurs at the duodenum, and at the duodenum there are specific receptors which are used to transport the iron across the villi into the blood, and from the blood it will go to the bone marrow, and from the bone marrow to the red blood cells. And here in the red blood cells, hemoglobin utilize the iron that is moved from the food that we eat on a daily basis. The red blood cells are carrying hemoglobin, which is an iron-containing protein, to be used the iron is used in the synthesis of hemoglobin, and that comes out in circulation to carry oxygen to various parts of the body. So for this isotopic technique, we use something called the common pool technique, wherein we take the meal of interest that we want to measure the iron absorption from, we add a tracer to that meal, we consume that meal, and that meal goes into the stomach and it undergoes the process of digestion. During the process of digestion, the iron from the food is released into the stomach along with the tracers that are present, and all of this interact together in a common pool. And whatever the enhancers and inhibitors are present in your stomach will also influence the tracer similarly as it would influence the dietary components. And then depending on those the enhancing and the inhibiting components and other ligands that are present within this common pool, the absorption of the iron would take place across the gut at the duodenum. It would enter the blood vessels, and from the blood vessels, it will go to various iron pools within the body. And the primary iron pool is the bone marrow, where the red blood cells are synthesized. So along with this iron that is going in, the tracer, a small amount of tracer is also absorbed, depending on the kind of absorption that meal has, and that would also go to the bone marrow. And within the bone marrow, new hemoglobin molecules are being synthesized and being packaged into red blood cells. Those new red blood cells that are being synthesized will carry the tracer within the hemoglobin and would come out into circulation over a period of 2 weeks. And when you take a blood sample from that person who has taken the tracer, and you subject it to isotope ratio mass spectrometry, you can then calculate what is the amount of absorption that has occurred from the test meal that you gave. So this is the principle of, or called the common pool principle, which we use in understanding iron absorption or measuring iron bioavailability in humans. So when you take a test meal of interest that you want to measure, add an extrinsic tracer that you have bought and to the meal, and then when you consume it, you would alter your isotopic composition in your body. Similarly, if there is more than one meal that you take, you can use another isotope of iron and consume it on subsequent days, and then you would alter your isotopic composition, which is slightly higher than what was for the tracers that are present already in your body. You can then measure this change or increase in isotopic composition using a mass spectrometer, and with that you can actually measure how much was your iron absorption. Yeah, so what does the mass spectrometer do is, the mass spectrometer, when you load up the purified sample from the blood that you have extracted, the mass spectrometer segregates the sample into its constituent atoms, and then based on the masses that we have in the body for iron, we will get the change in isotopic ratios from the mass spectrometer. And the important other factors that we need to keep in mind is the composition of the test meal, because depending on the meal that contains enhancers or inhibitors, the absorption can get influenced by the amount of these enhancers or inhibitors in the meal, the kind of meal, whether it is a liquid or solid, consumed before or after the test meal. I saw in the chat window, there was a question whether coffee or tea consumed before or after a meal can have an influence on iron absorption. Yes, certainly it can have an influence on iron absorption. What is the physical state of the subject, whether the subject is normal, has inflammation or infection, can all affect iron absorption. The kind of iron that you administer, the kind of chemical nature of the iron that you give, all of this thing can influence the bioavailability of the food. The other important thing to keep in mind is, in the selection of subjects for your bioavailability studies, you need to have a homogeneous population that you want to study. So you would want to match them for age and anthropometry. You want to have a similar iron status of all the subjects. You may want to study normal individuals, or you may want to study anemic individuals. You may want to study individuals in different physiological states. You may want to study pregnant women, or you want to study people with certain infection or inflammation. And for each of this, you may need about 10 to 20 subjects. And there are certain things you can control for. For example, the time it takes for the test meal that you have given, for the gut transit time, you cannot control for. There are certain the transport proteins that we spoke about, the DMT, divalent metal transporters, the density of that may be different in different people. We cannot control for that. And there could be undetected infection or inflammation, which we may not have we may not have taken into account, although we have done the measurement of their inflammatory markers. So you need to keep a good selection criteria, and also characterize these subjects for your studies in a way that gets you a good homogeneous population of subjects to reduce inter-individual variability. And you can add the isotope either extrinsically, that is, you can add the isotope just before your administration. You can add the isotope on the surface of the meal, or you can grow the plant with isotopic material added to the plant, and the plant grows with the isotopic tracer and produces vegetables or fruits with isotopes inside the fruit itself. Or you can isotopes to poultry, or you can grow small animals with isotope material, and then you will have meat and egg which can be isotope labeled intrinsically, although they are very expensive to do. So you can use, for most practical purposes, we'll use the extrinsic way of adding the isotope, because they are far easier and they're also cheaper to do, while intrinsic studies are also done, and we can do intrinsic labeling of the plants and animals to carry out studies. So you need to keep in mind that the ion or the isotope that you're adding should be in the same way as in the test meal. It cannot be very different. It should have about 20 to 30% of the total amount of ion within the total meal. And administration of the dose is also very important. We need to keep a track of all the dosing containers, the weights, and before and after consumption, we need to keep a very close document on the exact nature of the weights, so as to get exact amounts of the isotope administered. And we need to, if you're giving an intravenous dose, we need to keep the sterility of the compound that you're injecting, and a standby medical team to support you in case you're doing intravenous dose. So all these considerations are important in carrying out these studies. And there are some assumptions within the studies. We do take into consideration that 80% of the absorbed ion is incorporated into RBCs. This is based on certain earlier studies that we have done and from literature. And most of the RBC ion does not exchange with the plasma pool is another assumption, because hemoglobin ion is bound, and it does not exchange with the plasma pool. And we also need to have an understanding of the blood volume. And we can now use a standardized formula to calculate this. So these are the few assumptions within this technique. And to give you an idea as to how to measure what the test meal could be, it could be a simple test meal which is made of rice. And here in this question could be to understand what is the effect of adding a cup of tea along with your rice meal. So you would have one test meal which is administered with water, while the other test meal is administered with. So you could use the test meals to understand your question, and you can administer them on 2 subsequent days, followed by a gap of 14 days. You would take a blood sample at the baseline and a blood sample 14 days later. You could continue that for one more level by adding another dose of tea, and you can take a blood sample 14 days later. So you can then study dose response as well as the effect of tea on ion absorption. And you process the blood samples and extract or purify the ion from the hemoglobin, and then you analyze it on a thermal ionization mass spectrometer. So in terms of instrumentation, you need good weighing scales, good labware, which are Teflon labware. You need ultra pure water and acids, and you need a thermal ionization mass spectrometer, a clean room, and some reference material for doing your work. And from now on, I'll just quickly show you some of the work that we have done. We have measured the effect of tea on ion absorption, and you can see that all the absorption drops drastically with tea. And when you add vitamin C, you can see all the absorption increases dramatically. And similarly with calcium, when calcium is added to your meal, either from milk or any other milk products, you see that the ion absorption again decreasing. But the effect of calcium's inhibitory action can be overcome by the addition of ascorbic acid. And we did measure the absorption of habitual meals that is consumed in India based off rice, wheat, and ragi. And we saw that the absorption was highest when it was wheat-based and was accompanied with vegetables which are high in vitamin C. We also looked at infection. So you took a group of children and then who were Helicobacter pylori positive. We put them on antibiotic therapy and treated them, and post-therapy, you can see that iron absorption increases dramatically in these children. And very recently, we have taken finger millet, which is selectively bred for low phytic acid, and then use that for iron absorption study. And you can see that the finger millet with low phytate has a high iron absorption. And we also looked at a national program in India, which was giving enteric-coated iron tablets for all the anemic people. And we showed that iron absorption is poor with enteric-coated tablets. And we showed without enteric coating, the absorption is very high. And based on this data, the policy in India was modified to remove enteric coating from the supplementation program in India. And so with these, I would like to end my talk, and also to say that all further details on this technique is available in this manual. And thank you all.
So today, thank you very much for taking me home to Bogor for a couple of hours. And I would like to share with you some of the work that we have done in Thailand and in Indonesia. Just to remind you, isotope dilution is very similar to taking a liver sample. And so we all know that liver vitamin A is the gold standard. And so compared with other biomarkers, retinol isotope dilution is very much on the top. The different biomarkers measure different things in the human body. The most common biomarker, serum retinol, is measuring a static vitamin A concentration in the blood. The modified relative dose response is a test that was developed in Indonesia, working with my colleagues in Bogor, and it gives you a qualitative measure of liver stores. Retinol isotope dilution, however, can give you the total body stores of vitamin A in the body. In 1977, the first paper on isotope dilution was published. In that paper, it clearly states that the vitamin A level in blood is not sensitive to liver stores of vitamin A. But the world is still using serum retinol, especially for population surveys. It is static. It's found bound to a protein in the blood. It's decreased during infection. It's homeostatically controlled, which means that it will not necessarily change in response to an intervention unless you have serious vitamin A deficiency. A certain percentage is from recent dietary intake. And because of infection, serum retinol does not often respond. In dosing studies, you give either a dose of retinol or an analog. For dose response tests, you just need high pressure liquid chromatography. The isotope dilution needs mass spectrometry, and either you calculate a percent or a ratio. These are studies in children in Indonesia in the Bogor and Bandung area. And you can see that after intervention, serum retinol did not change. However, when we use the modified relative dose response test, liver stores significantly improved and we saw a drastic change in the ratio. Here are two villages in Bogor, and you can see very clearly that the vitamin A serum retinol concentrations are different. However, the means are both around 0.7, which would say that they both have severe vitamin A deficiency. But when you look at the modified relative dose response test, you see that one village has a more severe vitamin A deficiency than the other village. In the top graph, you see that there is one little girl that has vitamin A deficiency. And what we discovered in that particular instance is that girl had just moved into that village from a different village, and she hadn't been receiving the benefits of the village that was giving out free eggs. So you can see that a single food source can make a big difference in vitamin A status. For retinol isotope dilution, either deuterium or 13C is used as the stable isotope. Deuterium uses traditional GC-MS. 13C can use GC combustion isotope ratio mass spectrometry, which is similar to doubly labeled water, or LC mass spec. When working with 13C, which is what we use in my laboratory, you need to be cognizant of natural abundance, because this is important in deciding what the blood sampling will be. This is the synthetic pathway to add 13C to vitamin A. In our laboratory, we use 2 labels on the 14 and 15 positions in the synthesis, and then 1 micromole is given to children and 2 micromoles are given to women. So these are lower doses than the current recommended daily allowances for vitamin A. So we are truly giving tracer doses of the stable isotope. The principle of isotope dilution is that in some areas you must take a baseline blood sample. However, the baseline blood sample can be taken on a subset, and we have been involved in studies in Mexico and in Thailand, and the institutional review boards actually did not allow us to take this baseline blood sample. So we took it on other children. This was in our longitudinal studies where we have interventions. So there are ways around the baseline blood sample. Then you dose with the labeled vitamin A, allow 2 weeks for equilibration with the total body pool, and then take another blood. The math that is involved in the particular studies that we do are based on the mass balance equation. There are different assumptions that one needs to use. 80 to 90% of the dose absorbed. The lower value of 80% might be used in a population group that has a high level of inflammation, or if a reviewer makes you do it in your paper, which just recently happened to us. And then you use either 50 to 80% stored in the liver to calculate the total liver reserve. So the nuances are, this is the top equation, f of A minus f of C over f of C minus f of B is something called the tracer to ratio, tracer to tracy ratio. And that is what combines all isotope tests that are doing retinol isotope dilution. So you use 50% in the liver if you are working with a vitamin A deficient population, or 80% if you have adequate through hypervitaminosis A. We validated this test in rats using a variety of vitamin A statuses, and there was clear correlation. We also validated the test in hypervitaminotic monkeys, and there was 100% sensitivity to diagnose hypervitaminosis A. We applied the test to US women and found that it correlated with dietary intake, long-term dietary intake. So isotope dilution allows you to have a quantitative estimate of the mean vitamin A pool size, and it is best used in groups in a target community. It can respond to supplementation with known amounts of vitamin A, and it can be used to estimate the impact of vitamin A interventions. And if you are using a food, you can actually calculate the relative vitamin A equivalency of the provitamin A carotenoids. So the simple paired isotope dilution test is taking a blood sample and the first dose, waiting 14 days, deciding on your intervention length. In this particular instance, it was 90 days, allowing 7 days for equilibration of your intervention, and then taking a blood sample, second dose of isotope, and then another blood sample 14 days later. Sometimes you may want to use a positive and a negative control in your intervention. Here is an example of feeding orange maize versus white maize. And you can see we had a positive control group where we gave a dose of vitamin A every day that the children ate the biofortified food. We did a fortified rice study in Thailand, and the principal investigator is Siraporn Pinkau, and there were 50 healthy school children. Every day of school, so 5 days a week, they were given fortified rice in a single meal that contained 890 micrograms of retinol activity equivalents. There was a total of 60 days of feeding, and compliance was 54 days. As Cornelia showed you, there was a dramatic increase in total body stores of vitamin A in the intervention group. In fact, there was a doubling in the 54 days of this intervention, which meant that even though it resolved much of the vitamin A deficiency, reduced it by half, this was a very short period considering that most people in Thailand eat rice every day. We did a sensitivity and specificity analysis of serum retinol in this study. And what we found is that there was 0% sensitivity using the WHO cutoff for serum retinol of 0.7 micromoles per liter. Specificity was good, but this is sometimes difficult to interpret in population studies. We recently repeated the study with the same principal investigator, and she fed fortified rice to Thai lactating women. She enrolled 70 women, and 62 women had complete data sets, and 57 women had complete isotope analysis. I give you these breakdowns because you always need to increase your sample size to account for people who might drop out or for analytical losses, because it does occur with the sophisticated mass spectrometry analysis. We reduced the amount of vitamin A in the fortified rice in this study to 500 micrograms, which is similar to the EAR of women who are not lactating. Again, a single rice meal 5 days a week, and we fed for a total of 61 days. I show you these calculations because you need to make another assumption when you are working with lactating women. We actually were able to calculate the half-life of vitamin A in these women, and it was 56 days. So for lactating women in Asia who are vitamin A deficient, 60 half-life for vitamin A. And in during lactation, you also have to make the assumption that 20% is lost to the breast milk. So this is a different assumption than what you would use in women who are not lactating. So our results were very similar as we have found in other studies. We found a change in total body stores of 52.9 micromoles, and there was actually a negative finding in the control women during this time. We found that the average women was vitamin A deficient, and 50% of them were vitamin A deficient at baseline, and this was reduced to almost half in the lactating women. We moved on to determining vitamin A requirements in our laboratory. And we fed women of reproductive age 3 different levels of vitamin A for 42 days. And we did this with a highly controlled diet that only contained about 150 RAE each day. And then we gave randomized supplements, either 0, 175, or 525 retinol activity equivalents. What you see here is where the line crosses the 0 line. That is the estimated average requirement for this group. So you see that it is somewhere between 200 and 300 RAE per day. And you might be aware that the actual RDA for the US women is 700. So that is grossly overestimated. So you can see that actually determining the estimated average requirements can be done with isotope dilution methods. We tried to do this in Bogor, and we were not successful. So you'll say, well, why weren't you successful? That doesn't make sense. We did not have the facilities to have a highly controlled diet. And we only had 2 dose levels, 0 and 525. And also the women were very vitamin A deficient. So in that particular instance, we were not successful in actually estimating a requirement. So there are things that we need to keep in mind when we are designing different studies. First, you need to work very closely with your collaborators because there is key information that you need to know. First of all, one main question, do you need a baseline blood sample on everybody, or can you get away with only having either a single blood sample in an evaluation or 3 blood samples in an intervention? Oftentimes, public health researchers are very interested in that baseline blood sample. So sometimes it is part of the protocol. But just keep in mind that in some studies, you may not need a baseline blood sample on everybody. What also is very important is the volume of serum needed for your analysis. In our laboratory, we have reduced this volume, but we need 400 microliters of serum for our analysis. We recently have started doing analysis of a vitamin A fortified oil study in children in Indonesia. And the reason we hadn't analyzed these samples earlier was because we needed 700 microliters. We have improved upon that, but even some of the samples that we received from Bogor only have 200 microliters. So we won't be able to analyze them. There are different types of mass specs. Our particular mass spec needs mass in order to analyze. Does your study design need a controlled diet? To answer the research question. Now, we saw this in the American study versus the Indonesian study. If you are looking at requirements, you really have to have a controlled diet. And I'm talking about breakfast, lunch, and dinner 7 days a week in order to do estimated average requirements. So then at what points? If you are only interested in vitamin A status, you only need to control the diet during the mixing period. If you want to have very clean data. However, you can also use an assumption of 0.8 in your equation and not restrict the diet. So in conclusion, stable isotope techniques are very powerful. They can assess bioavailability and bioefficacy and lead valuable feedback on the impact of vitamin A programs. Does the intervention work in a controlled trial? That's efficacy. Does the intervention work in practice? That's effectiveness. And then efficiency. Is the cost worth the investment in individuals and in society? So which biomarkers are you going to use? I believe that the world can move beyond serum retinol concentrations to evaluate interventions and set policy. A few years ago, Indonesia started fortifying vegetable oil. And we have seen an impact using the modified relative dose response. Now it might be time to look at retinol isotope dilution as an evaluation tool to see how total liver reserves have improved for this intervention. The interim was to give vitamin A supplements to preschool children every 6 months up to the age of 5 years. What we have found in countries such as South Africa and Zambia, who now have fortified foods available, it is very easy to actually accrue high levels of vitamin A leading to bone interference. So it is very important that you evaluate the public health programs that you have in your country. So with that, I will leave it and I'm happy to answer any questions.